Welcome to session 1. Let me start with a situation that almost every data scientist eventually faces. You work in a notebook for 2 hours. You load the data, you try a few things. You delete some cells. You rerun a few cells. You change a variable. You train a model. And finally, everything works. You save the notebook and send it to somebody else. They open it and click run all. And it fails. Or something even more dangerous happens. It runs but gives a different answer. So our question today is what changes when an analysis has to be rerun, reviewed and trusted by someone else? And the important point I want you to remember from the beginning is this. A notebook that ran successfully once is not automatically reproducible. Think about some of the notebooks you have created. Have you ever had something like cell 15 working only because you previously ran cell 27? Or maybe you changed a variable somewhere, reran one cell, and everything started working. That happens because notebooks maintain something called state. When you execute a cell, variables and objects remain in the computer's memory. Even if you later delete the cell that created the variable can still exist in the memory. So your notebook might look perfectly fine while secretly depending on something that is no longer visible. Today we are not trying to create the world's best machine learning model. We are going to do something more fundamental. We are going to turn a notebook into a workflow that another person can understand and rerun from the first cell to the last cell. Before writing any code, let's clarify two terms, repeatability and reproducibility. We will use a practical distinction. Repeatability means that under the same setup, I can execute my workflow again and obtain the same result. Reproducibility goes one step further. The workflow is organized and documented well enough that somebody else can understand what I did, rerun it, and obtain the same or an acceptably equivalent result. Different scientific communities sometimes define these words slightly differently. For notebook work, this distinction is useful. Now, why do notebooks become unreliable? Usually because of four things. First, cells have been executed out of order. Second, configuration values are scattered throughout the notebook. Third, paths are specific to one person's computer. And fourth, randomness is uncontrolled. Imagine I execute the cell threshold equal to 60 and later I accidentally delete the cell. But because I have not restarted my runtime, threshold is still sitting in memory. So this might continue working. So let's say I delete this and then try this. So this line will continue working because threshold is defined. So this is our notebook. I will be sharing the notebook in the GitHub repo. The point is simple. even when threshold is not visibly in the notebook. Then also uh, the second line which involves using threshold will run because it is saved in the memory. So someone else opens the notebook, they do not have that hidden variable, so their notebook fails. That is why one of the most important habits is restart runtime and run all. Not because pressing run all is some magic ritual, it is a test. It tells us whether the notebook really contains the dependencies required to recreate its result. Another problem is scattered configuration. So this is the restart and session run all button which we press to test the notebook. That notebook will be usable to someone who simply reviews it or maybe uses it. So another problem is scattered configuration. Maybe the data path is in cell 2. The target variable is in cell 14. The test size is hard coded in cell 25 and the random seed is hidden somewhere else. Instead, we will create one configuration section. We will not leave it as a scattered configuration, but we will create one configuration section. The third is randomness. Many data science operations involve randomness. Sampling involves randomness. Train test splitting can involve randomness. Random forests involve randomness. Some optimization algorithms involve randomness. If we allow all of those things to change every time we execute the notebook, our results can change too. So when repeatability matters, we explicitly control randomness using things such as a seed or a random state. For example, seed equal to 42. It can be any number. So let's start with a messy notebook. Here is our notebook. This notebook represents something quite realistic. There are duplicated imports. There is a hard-coded slash content path. So this import you can see is duplicated. The path is hard-coded. This content part is hard-coded. Some cells depend on code below them. Configuration values are mixed. Configuration values are mixed into the analysis, and our machine learning model contains uncontrolled randomness. None of these problems necessarily mean that the analytical idea is incorrect. The problem is that the workflow is unreliable. So we are going to organize the notebook into 8 sections. So first is display. So these 8 sections are these. First is setup and configuration. Then second is load data. Third is validate data. Fourth is explore. Fifth is model. Sixth, evaluate. Seventh, save outputs. And eighth is conclusion. The important property here is that every section should depend primarily on sections above it. The notebook should read from top to bottom. So here is the first section, setup and configuration. First, all our imports are together. We don't want to import pandas in cell 2, again in cell 15 and again in cell 28. Someone looking at the notebook should be able to quickly understand its dependencies. Now create the configuration cell. This cell is extremely important. Look at what we have collected here. Our random seed, our data path, our output directory, our test size, our target variable, and our feature columns. Suppose tomorrow I decide that instead of a 20% test set I want 25%. I change one line. Test size equal to 0.25. I don't have to search through the notebook. I am also using Python path object rather than manually creating file path strings. It makes our file handling clearer and more portable. Now we create a dedicated loading section. Notice the explicit file check. You could simply call pd.readcsv, but think about the person running your notebook. If the dataset is missing, I want the notebook to fail immediately without meaningful explanation. I don't want an unrelated looking error 10 cells later. Let me load the data. Now let me rerun it. Before we explore or model the data, let's verify the assumptions that the rest of the notebook depends on. Our notebook expects certain columns. Let's explicitly check that they are there. We are assuming every learner ID is unique. Let's test that assumption. We are assuming that the model columns do not contain missing values. Let's test that too. And because final score represents a score from 0 to 100, let's explicitly check its valid range. This is an important mindset change. Instead of keeping assumptions inside our heads, we are putting some of them into executable code. Validation is not the same thing as cleaning the dataset. We are simply asking, are the assumptions required by the rest of this workflow actually true? Now that our data has passed validation, we can safely begin exploration. We are intentionally keeping the exploratory analysis small because today's session is not EDA. I just want us to have a real analytical workflow to organize. So let's create one plot. Here's another useful convention. Our exploration section is examining the data. It isn't secretly redefining the target, randomly filtering rows, or changing configuration values. If exploration causes us to make an important analytical decision, that decision should eventually become explicit in the workflow. Now we reach an important reproducibility issue. What do you think random state equal to seed is doing here? Train test split randomly decides which observations belong to our training set and which belong to our test set. Without controlling that randomness, the rows in our test set can change between executions. That means the evaluation can change even though our code apparently did not. We are also giving our random forest the same random seed. There is an important nuance here. A fixed seed does not mean that every computation will necessarily remain bit for bit identical forever across every possible operating systems, hardware configuration, Python version, and library version. There are other sources of variation, but explicitly controlling randomness removes a major source of accidental variation and clearly documents our intention. Evaluation gets its own section. The exact model quality is not our concern today. What I want you to notice is how we connected the important output into one named object. This is easier to inspect, store, and compare than several disconnected print statements. Finally, if something is an actual result of the workflow, let's save it deliberately. Now the result isn't something that existed briefly as output under cell 25. We explicitly know that our workflow produces and what our workflow produces and where it produces it. Now we are going to perform the most important operation of this entire session. We are going to restart the runtime. Restart kernel runtime. So let's just restart it for the time being. Everything that existed only in memory has now disappeared. You can notice that the number written there was number written previously when it was run, but now that number is has disappeared. Now let's select run all. Now watch the notebook execute from the first cell to the final cell. If everything succeeds, we have gained much stronger evidence that the notebook's visual workflow actually contains its dependencies. And because we have controlled the important sources of randomness in this example, our metrics should remain stable. Now it's your turn. I have given you the messy version of this workflow. I do not want you to improve the random forest. I do not want feature engineering. And I do not want you to spend time trying 10 different algorithms. Your task is simply make this notebook cleanly rerunnable without changing its analytical question. So they are intentionally common notebook problems, duplicate import, a hard-coded path, cells depending on code below them, configuration values mixed into analysis, uncontrolled randomness, and output generation code mixed into evaluation. So this will be the desired architecture: setup, load, validate, explore, model, evaluate, outputs, and conclusion. Give yourself around 5 minutes, and while you work, keep asking yourself one question: if I started the runtime right now, what would break? Which values belong in configuration? Where exactly does randomness enter this notebook? Does this cell depend exclusively on something that has already happened above it? Is this cell loading data, analyzing data, or producing an output? Can you tell clearly? So pause the video and continue it. Try to do it on your own. Now stop coding. This is the interpretation checkpoint. So why is a notebook that ran once not automatically reproducible? Answer that in one sentence. And try not to simply say because it might not work. Tell me why. So a notebook that ran once is not automatically reproducible because its result may depend on hidden state. environment specific assumptions, or uncontrolled randomness that are not captured in the visual workflow. So you don't have to memorize my sentence. Your sentence might say, because previously cell executions or machine specific settings might be affecting the result. That is perfectly fine. So write down your one sentence interpretation in the comments. What matters is that you recognize the difference between I once obtained this output and I have captured the process required to recreate this output. So let us finish with 7 ideas. So a reproducible notebook is one configuration section, clear data paths, validate important assumptions, control randomness, top to bottom dependencies, save outputs intentionally, restart plus run all to test. So first, restart and run all is a test, not a ritual. It helps us discover hidden state. Second, put configuration in one place. Paths, seeds, feature names, target names, and important parameters should be easy to find. Third, validate assumptions clearly and early. If your analysis requires a particular column, don't discover that it is missing halfway through model training. Fourth, control randomness when repeatability matters. Use a seed or random state whenever the relevant library exposes one. Fifth, make dependencies flow from top to bottom. A reader should not need cell 35 before cell 12 can execute. Sixth, save important outputs intentionally. A result should not survive only as notebook output. And seventh, after making important changes, restart runtime and run on. One final clarification, I am not saying that every data science notebook in the world should use exactly these 8 headings. As projects become larger, some work will move into Python modules, configuration files, pipelines, experiment trackers, and other systems. Our underlying principle is much more important. The structure of our analysis should make its dependencies visible. So today's answer to our core question is once an analysis needs to be rerun, reviewed, and tested by someone else, writing code that works is no longer enough. We need to make the process that produce the result explicit. In the next session, we can take this one step further. Today we asked, can I reproduce the analysis? Next we can ask, can I trust the data entering the analysis?